Hello viewers, welcome to today's lecture on signal conditioning circuits. In the last lecture, we have discussed different types of transducers which are used for interfacing with the physical world. And today we shall discuss about the signal conditioning circuits. Let us try to understand why do you need signal conditioning circuits. As you have discussed, we use transducers for converting energy. So here are your transducers. For converting energy from some physical form. That physical energy, as you have seen, can come in the form of temperature, pressure, flow, light, and so on. This energy is converted into some electrical form with the help of transducer. So here it is electrical form. But we have seen that this electrical form can be either current, voltage, or it can be some resistance. All the three are essentially electrical parameters. And in most of the situations, these current levels or voltage levels are not really very high, low level. Usually these are of low level. And also the resistance value can vary from large to very small. Now, this electrical signal ultimately has to be applied to one analog to digital converter, ADC, which will convert the analog signal to digital form. But as I have said, the analog to digital converters have some voltage range, say from 0 to plus 5 volt or plus 5 to minus 5 volt, and like that in the range of volts. So to get these electrical signals in this range and also to convert from one energy to another, you will require a special circuit which is known as signal conditioning circuit. This is your signal conditioning circuits. So what this signal conditioning circuit will do? The signal conditioning will perform. So what is the function of signal conditioning circuits? Let us try to understand. Function of signal conditioning circuits. First of all, it has to provide some kind of interface or isolation. Why do you need interface or isolation? The transducer may be producing some resistance or current or some voltage. That has to be isolated by high input impedance, so that the transducer characteristic is not affected because of this interfacing. So you require some kind of interfacing or isolation so that the transducer faces high input impedance, or in other words, the transducer operation is not disturbed because of the interfacing. What are the second requirement? As you have seen, the transducer produces very low level voltage or current, or resistance value can be very high. So you have to convert the voltage level to some higher level so that it is compatible with the analog to digital converter. So you will require amplification so that the voltage level voltage level is compatible with the analog to digital converters, and you get proper accuracy and so on. So amplification is one requirement. Second requirement is you have to convert, say, current to voltage conversion. Usually the analog to digital converters will require input in voltage form. So you have to convert the current to voltage form if the transducer produces current. So you will require current to voltage conversion, and that also has to be done by the signal conditioning circuit. And also you have to do resistance to voltage conversion, resistance to voltage conversion. We have seen some of the transducers produces resistance depending on the physical parameter value, and the resistance value changes. But the analog to digital converter will require a voltage, and that voltage should be proportional to the resistance. So it will do resistance to voltage conversion, that interface hardware. And also sometimes you will require level translation. Level translation. You will see sometimes the voltage levels are not in this range, say 0 to 5 volt or -5 to +5 volt or something like that. So in such cases you have to translate the level, maybe sometimes it is say -12 to 0, or maybe very high voltage level. So in such cases you have to perform level translation. So the basic function of the signal conditioning circuits are these. Question arises, how do you do this kind of signal conditioning? What kind of device you will require for this purpose? The most popular device which is used for signal conditioning is known as operational amplifier. And so you will see it is the most common building block of signal conditioning circuits. And that's why today we shall first discuss in detail about the operational amplifier. What we shall study what is operational amplifier and how operational amplifier can be used for performing signal conditioning in different situations. Let us try to understand what do we mean by operational amplifier. Operational amplifier is an integrated circuit, is an IC which has got two input terminals. One is known as negative input, one is known as positive input. It has got two more terminals for supply voltage, V plus, V minus, and output. So it has got differential input, single ended output, and the differential inputs are negative input and positive input, and V plus and V minus. And in addition to this, it has got some ideal features. Ideal features. Let us see. Let us try to understand what are the ideal features. The ideal features are, first of all, input impedance. Input impedance here is assumed to be infinity. So ideally the input impedance should be infinity. Later on we shall see usually it is not infinity but some high value. So let me list out the ideal features first. Input impedance is infinite, output impedance 0, that means here it gives you output impedance 0, then your voltage gain is infinity, then bandwidth is also infinity, then perfect balance. Perfect balance means whenever the V output is 0, whenever V in, V negative, that means this V negative is equal to V positive. So these are the V in negative and V in positive are same. That means whenever you apply same voltage to these inputs, output is 0 and there is no drift. There is no drift. So these are the ideal characteristics, but in practice this is not so, because input impedance is never infinite. So in reality the real values are somewhat not exactly same, but for all practical purposes we can assume that these ideal conditions are satisfied. So input impedance has been found to be very high, say of the order of 10 meg ohm, which may be considered to be fairly very high. Output impedance few ohms. Then output impedance voltage gain has been found to be about 500,000, very good, very high voltage gain. Bandwidth is from say 0 to it can be 10 megahertz, and offset can be very small like 10 microvolt, and with drift of about uh, say 5 microvolt per degree centigrade. So drift is also very small. So these are the typical characteristics of op amp, and you may be asking why the name operational amplifier. As we shall discuss, these operational amplifiers can perform various arithmetic operations in analog domain like addition, subtraction, then your integration, differentiation, and so on. That's why the name operational amplifier, or in short op amp. So usually it is called as op amp, operational amplifier, and that is the reason why operational amplifiers are used not only in realizing signal conditioning circuits, they are used in realizing analog computers. So in analog domain it can perform various operations, that's why this name. Now let us discuss how this operational amplifier can be used to realize different types of circuits. Let us start with inverting amplifier. Inverting amplifier can be realized in this manner. Say this is the op amp, and here is the negative input, here is the positive input, and this is your supply voltage minus. So whenever you use as inverting amplifier, you apply a voltage V in through a resistance R1, and there is a resistance between output and the input, and this input, positive input, is connected to ground. So whenever positive input is connected to ground and you apply a resistance R2, then you will get a voltage V0 here. Now you can make detailed analysis to find out this output voltage, but we can use some thumb rule to find out the output voltage by using simple properties of the operational amplifier. As you have seen, the input impedance is very high, so it draws no current. No current is drawn. That's why whatever current comes to this, sum of the current to this will be 0. Current flowing out, flowing in, and so on. The sum of the currents, if you take, it will be 0. So if we do apply that rule, then V in by R1, that is the current going in this direction, and we don't know, let the output be V0. So V0 by R2, that is the current, since this is connected to negative input and positive input is connected to ground. So this input should also have the same voltage. That's why it is called virtual ground. So since this voltage is 0, the voltage, because of this voltage, the current flowing through this will be V0 by R2, and since no current goes to this input, the sum of the current will be 0. So from this equation we can get V0 is equal to minus V in R2 by R1. So by choosing suitable values of resistance, you can use it as an amplifier, we have seen. And for example, if R2 is equal to say 100 k ohm and R1 is equal to 10 kilo ohm, then you get a gain of say 10. So in this way you can use it as an inverting amplifier. You may be asking why I am calling it inverting amplifier. The reason is the polarity of the voltage at the output is negative, opposite phase. So if you apply positive voltage, you get a negative voltage. If you apply negative voltage, you get a positive voltage. The reason for that is here the current direction is this, from, if it is positive voltage, from this point to the virtual ground, and at that time the current will be going out. Since it does not take any current, it goes out. So since the current is in this direction, this will be negative with respect to this point. So you get a negative voltage. So this is your inverting amplifier. In this way you can realize a non-inverting amplifier. Let's see how it can be done. The circuit is somewhat like this. You will use, since it is an non-inverting amplifier, you have to apply the input to positive input. So you will apply V in to this input, and this input will be, this resistance R1 will be connected to ground, and this is your R2. So in this case V out will be equal to V in into R2 plus R1 by R1. So this can be also proved very easily. You see, since these two inputs should have the same voltage, equal voltage, here we will get V in voltage. To get voltage V in, these two resistors will act as a voltage divider. So the voltage across this is V0 into R1 by R1 plus R2, and so from this you will get V in is equal to, is following this relationship. So here also you can choose different values of resistance, so that you get a voltage gain, and as you can see here, voltage gain is always 1, more than 1 in this case. This non-inverting amplifier can be modified little bit to realize unity gain amplifier. So for example, here you can apply this one to V in, and these two are sorted, say negative input and output is sorted. So negative input and positive output is sorted. So this one here, V output will be equal to V in. That's why it is called voltage follower. Similarly, in this case, if you want unity gain, you have to simply make R1 is equal to R2. So whenever it is R1 is equal to R2, in this inverting amplifier, the gain is unity. So we see here how the op-amp can be used as an inverting amplifier and non-inverting amplifier. Then you can extend the idea of this inverting amplifier to realize summing amplifier. Let's see how the summing amplifier is realized. In a summing amplifier, you will realize in this manner. Here is your op-amp. So negative input, positive input is connected to ground, and this is your negative input, and there is a feedback resistance which is equal to RF. Then you can put several inputs here. For example, let's take two inputs. This is your V1 and this is your V2. V1 is connected through a resistance R1 and V2 is connected through a resistance R2. So whenever you do this, you can use the same logic. This current will flow through it, this current will also flow through it. So V out that we will get here will be equal to minus RF into V1 by R1 plus V2 by R2. So in this way you can add several such inputs. You can go up to say Vn, and this is your Rn. So in this way you can have up to n inputs plus Vn by Rn. So here it is summing the inputs, summing the currents and generating a voltage which is proportional to these voltages. If Rf and R1 are same, say Rf is equal to R1 is equal to R2 plus Rn, then that means if Rf is equal to R1 plus is equal to R2 is equal to Rn, all are same, then V0 will be equal to minus V1 plus V2 Gn. So you see it is performing addition, analog addition. All the voltages are added together and it produces a voltage, of course with opposite polarity. Then you can put one another inverting amplifier of unity gain to get this voltage of the same polarity. So we have seen here how you can perform addition by using operational amplifier. And there are many signal conditioning situations where you have to perform this kind of summation operations or addition operations. And similarly, you can realize difference amplifier in this manner. You will require two inputs. One is connected to the negative input, another to the positive input. So here, let's assume this is V1, this is V2, and this is R1, this is R1, and another resistance is connected here. This is R2, and this is also R2, which is connected to ground. So I have not drawn the supply voltages, which will be always there. Then it gives you a voltage output V0, which will be equal to V2 minus V1 into R2 by R1. So here it is acting, if R1 and R2 are same, then it will act as some kind of subtractor or difference amplifier. So it can perform subtraction, you can say, in analog domain, or it can produce a voltage which is proportional to the difference of the two voltages applied here. So this is how difference amplifier can be realized. But in many signal processing applications, you require better kind of amplifier which are realized by using instrumentation amplifier. Here an instrumentation amplifier is realized by using three operational amplifiers. These three operational amplifiers will perform the instrumentation amplifier. It is produces voltage V0. Here one a voltage is applied, that is positive to the positive input. Here also it is applied to the positive input. And you can see here the negative inputs. To the negative input there is a resistance in the feedback path. So another feedback path. So here it is a non-inverting amplifier, another non-inverting amplifier, then these two are together connected to another difference amplifier. And by using the same technique, the output voltage here can be found out, that is V0, that will be equal to V2 minus V1 R4 by R3, the ratio of these two resistors, into 1 plus 2 R2 by R1. So you see here this factor is constant, because once these resistors values are chosen, this factor is constant. So it produces a output which is proportional to the difference of these two voltages. However, in addition to this, it has got a number of additional features. That's why this instrumentation amplifier is widely used in many applications. Let us see what are the important features of this instrumentation amplifier. First of all, it has got high gain accuracy. You can realize a difference amplifier by using this, by using a single op amp. But whenever you use three operational amplifier in this form, it gives you better, high gain accuracy of the gain is higher compared to the use of single operational amplifier. Then another important parameter which is important in many applications, that is your high common mode rejection ratio. Common mode rejection ratio. Let us try to understand what do we mean by common mode rejection ratio, which is commonly called as CMMR, common mode rejection ratio. Suppose the voltage here is -1 volt, to this input. V1 is equal to minus 1 volt and V2 is plus 1 volt. So the difference between these two voltage is 2 volt. With 2 volt of voltage difference, you will get some voltage here depending on these resistance values. Now, what you do, you make V1 is equal to 1 volt and V2 is equal to 3 volt. So here you see the voltage difference between the two is same, 2 volt. However, it has been found that in many situations like this, although the voltage difference is same, but if the levels are different, say 1 is plus 1, minus 1, minus 1, plus 1, or 1 and 3 volt, difference is same, you will not get the same output. But in this particular case, whenever you use 3 operational amplifiers, it gives you better common mode rejection ratio. In other words, in this situation, in this condition, in this case 1 and case 2, you will get more or less the same output. That's why we call it high common mode rejection ratio. That means the common mode rejection takes place and you get the accurate output voltage. Then this also, because of lot of feedback, it provides you high gain stability with low temperature coefficient. Low temperature coefficient. Then another property is low DC offset, because as you can see here, the operational amplifiers are connected directly without using the blocking capacitors. As a result, there is some DC offset, but whenever it is connected in this form, it gives you low DC offset, and also it gives you low output impedance. Low output impedance, which is an important property. So because both of them are connected to positive input, it gives you high input impedance. So that I have not written, high input impedance. Low output impedance, and many other additional features which are very close to the ideal. We have already seen the ideal features of an operational amplifier, not this one. We have seen the ideal features of an operational amplifier, which is here. So this instrumentation amplifiers helps you to realize amplifier which is very close to an ideal operational amplifier. That's why this instrumentation amplifier is widely used in many applications whenever you have to amplify the difference of two signals. Later on we shall see its uses. For example, one important application of this is, say, in strain gauge applications. Strain gauge application. Here we have seen that the value of resistance that strain gauge gives is very small. Now the difference in resistance has to be amplified. Normally it is arranged in the form of a bridge. So this is the resistance whose value is changing, which is very small, and these are some other resistances, standard resistances. Now you apply some voltage here to a bridge, say positive, negative. Now this is connected to an instrumentation amplifier. So this is your instrumentation amplifier. Instrumentation amplifier means, I use this. So that means V1, V2. That means this is your V1, this is your V2, and you get V out. So instrumentation amplifier is used in this situation because the change in small resistance that can be measured with the help of this bridge arrangement, and this output gives you the voltage which is proportional to the current flowing through the resistance, or the change in resistance that is taking place, that gets translated into voltage here. So we have seen one important use of instrumentation amplifier. There are numerous other applications where this instrumentation amplifier is used. Now let us consider some more applications of operational amplifier. One is current to voltage converter. So current to voltage converter can be done very easily with the help of operational amplifier. Say here is your op amp, operational amplifier, and this positive input is connected to ground, negative input is connected to feedback to the output, that is your VO, and this is your RF, feedback resistor. Now to this input you apply I in, that current. So the current will pass through this since this input, negative input, does not draw any current, it will pass through this feedback resistor and generate a voltage, and this voltage output will be equal to minus I in into RF. So here, as you can see, it is the output that you are getting is a voltage, although the signal that you are applying here is current. So this particular circuit is converting current to a voltage. And in the last lecture we have seen there are many transducers which produces current. For example, a photodiode. Let's see how a photodiode current can be converted voltage. This is your photodiode. This is a photodiode, and let me connect it to ground. This is applied to the negative input of the op amp, and positive input is connected to ground, and here you apply resistance RF, and here you will get a voltage V0. So since the current will flow in this manner, in this case the current will flow in this manner, and as a result the current that it draws, corresponding to that you will get a voltage RF. So if this circuit will produce a output voltage which is equal to that reverse saturation current into RF. So here is an application where the operational amplifier is converting the reverse saturation current of the photodiode into a voltage. So this can be applied to analog to digital converter, and you will get a corresponding digital value. So here we see how the signal conditioning is done by an op amp, and it is converting current to voltage. Then comes the voltage to current converter. You can use it to convert voltage to current also whenever necessary. For that purpose the circuit will be like this. So this is your op amp, negative input, positive input is connected to ground, and here we use a resistor R. Then here is your V in, and this is connected to this output. Now this output, there you can connect it to some resistance. Some resistance can be connected here also, or load. Now in this particular case, you see here it will produce this has been connected in such a way that this output and this output is same. That means the negative input and output V out V0, they will be same. As a consequence, there will be current flow through this resistance, and the current that will be equal to that current I that is passing through it will be equal to proportional to IL will be equal to, this is your IL, will be equal to V in by R1. This is your V by R1. This is your load. So here it will produce a voltage of V0. So current flow that will be equal to, actually not through this, here it will be current will flow through it. So our load, this current will be proportional to the that V in by Rn. So the current is converted, the voltage is converted into current. The current flowing through this resistance is proportional to the voltage. So here it performs the voltage to current conversion. So this is also used in many situations. Now as I said, not only addition subtraction, it can also perform two more important operations, that is your integration and differentiation. So integration can be done in this manner. So here is your op amp, then you have got the resistor, feedback resistor connected to it. This is your R1 and there is a capacitor here, and this is positive input, negative input, this is connected to ground, and this is your V output, and here you apply V in. Sorry, this is not an integrator, this is a differentiator. I have drawn it longly. This will be the differentiator. This is the differentiator circuit. So this is a differentiator, and what will be the output? This out can prove that the output will be equal to V output in this case will be equal to minus RF C1 into dV in dt. That means the time constant is decided by this C1 into this is your RF, and the rate of change of input voltage here is here you get a voltage depending on the rate of change of voltage here. That's why it is called differentiator. And in fact, this circuit can also be used as a high pass filter. Why it is being used as a high pass filter? As you can see here, this capacitor acts as a low resistance in higher frequency, but this resistance this offers same resistance for high frequency as well as low frequency. As a result, gain of this circuit will be high for higher frequencies, because the gain is decided by impedance of this by the impedance of this, and at lower frequencies this resistance, the impedance of this capacitor is high. As a result, the gain will be less. So the typical characteristic will be somewhat like this. So high pass means it will allow so high pass, that means it will allow upper frequencies to pass easily. Now let us consider, this is the use of the operational amplifier as a differentiator, and as I have told, it can be used as a high pass filter. Now it can be also used as an integrator. Let us see how it can be done. In that case, the resistance and capacitor positions are to interchange. So you apply V in to the resistor R1, and then this is applied to the negative input, and positive input is connected to ground as usual, and the capacitor is connected here between the output and the negative input. So this is your C1. So in this particular case, the V output will be equal to the minus 1 by RC, R1 into C1, and integration of V in dt. So if you apply a DC voltage here you will get, suppose you apply small DC voltage here, then here you will get a ramp, the output will continuously it will increase because of this integration. So this integrator has many applications, as we shall see, particularly later on we shall discuss the realization of analog to digital converters. There you will see this integrator can be used to realize analog to digital converters. So not only this circuit can act as an integrator, it is used also as a low pass filter. That means the characteristics will be, that means this is your frequency, this is your gain. So here it is your gain, this is frequency. Low pass means the characteristics will be somewhat like this. Depending on the value of R1 and C1, this particular point will be there. So this is a single order low pass filter, this is a single order high pass filter. So these are the two interesting use of operational amplifier to realize differentiator and integrator. And as I told, these operations, integration, differentiation, these were earlier realized by analog computers. So that's why these op-amps are commonly used as a building block for realizing analog computers. Now let us consider another interesting application, an example in which the op-amp is used as a level translator. Let us consider the problem. The problem is design a signal conditioner using op-amp for interfacing AD 590 IC temperature transducer to produce 0 volt at 0 degree centigrade and plus 10 volt at 100 degree centigrade. Now in the last lecture we have discussed the characteristics of AD 590, and there we have seen it is a PT80 device. It gives you 0 current in at 0 degree Kelvin, and the current it gives you at the rate of 1 microampere per degree K, and at that rate increases. That means at 0 degree Kelvin it gives 0 microampere, and as the current increases it will produce higher current, and it will increase at the rate of 1 microampere per degree K. Now how we shall design a circuit like this? Let us see what kind of current it produces at 0 degree centigrade. So at 0 degree centigrade, since it produces 1 microampere per degree centigrade or per degree Kelvin, it will produce 273.2 microampere, because that means the temperature is 273.2 Kelvin, that is your 0 degree centigrade. So 1 microampere per degree K, it will produce this current. Now we have to produce 0 volt whenever it is producing this current, and at 100 degree centigrade it will produce how much current? It will produce 273.2 plus 100 microampere. So essentially what you have to do, this current will be translated to 0 volt, this current has to be translated to 10 volt. How we can do that? That can be done with the help of an op-amp circuit. Let's see how it can be done. This is the op-amp, negative input, positive input. Now first of all, let us see how we shall connect this AD 590. AD 590, and whenever this current is produced, no current should pass through this op-amp. First of all, we have to use feedback resistor here, and two resistances. One resistance is connected to say some reference voltage plus 2.5 volt, and AD converter, that is AD 590, which is a two terminal device, is connected here and connected to some V minus voltage, to some negative voltage, say minus 5 volts, let us assume. So this is connected to ground. Now at 0 degree centigrade, this will draw current, this will draw this much current. Now if we choose a resistor such that this much current will be generated by this and pass through it, so that no current flows through it, then it will produce 0 volt. So the we can take a nominal value of 4.7 kilo ohm, then adjust it, and so that the current passing through it is 2.5 volt. So current passing through it is 273.2 microampere. So this is virtual ground. So very easily this resistor can be adjusted. That means 2.5 by this resistance has to be 273.2 microampere. That can be done by putting some fixed resistor, say 6.8K. So the value should be close to 10K. So for 6.8K fixed resistor is used, and a variable resistor preset potentiometer is used to adjust it so that it produces the current 273.2 microampere. This much current is produced. Now you have to convert 100 microampere to so difference is 100 microampere to 10 volt. So what will be the value of the resistance? You will require 100K. So here also we put one fixed resistors 82K and another preset pot, say 22K, and adjust it to get about 100K, so that you get the output of 10 volt whenever the current that it produces is 100 microampere. So you see, this op amp is performing several functions. First of all, it is acting as a current summing amplifier. That means this current and this current it is summing to produce a 0 volt. This current is coming in this direction and this current is going in this direction. So here no current is drawn. So it is performing current summing by making this point a virtual ground, and then whenever it is drawing more current, 100 microampere more current, that current is converted into voltage here, and you will be getting plus 10 volt whenever the temperature is 100 degree centigrade. So you see, the AD converter produces 0 volt microampere at 0 degree Kelvin, 373.2 microampere at 100 degree centigrade, but this output of the op amp will produce 0 volt at 0 degree centigrade and 10 volt at 100 degree centigrade. So here is an example of the signal conditioning circuit performed by an op amp, which produces the required voltage. It converts from current to voltage, it performs summation, and also does the proper scaling. That means, so it can be applied to an AD converter, ADC, with full scale range of 0 to 10 volt. So we can summarize our lecture by saying that in today's lecture we have discussed how we can realize signal conditioning circuit with the help of operational amplifier. We have discussed the characteristics of operational amplifier and its different applications, like as a inverting amplifier, non-inverting amplifier, integrator, differentiator, current to voltage converter, voltage to current converter, and also we have illustrated with an example how the signal conditioning can be done with the help of operational amplifier. So in the next lecture we shall discuss, in the later on, may not be in the next lecture, after 1 or 2 lecture, we shall discuss how the output of the signal conditioning circuit will be converted from analog to digital form with the help of analog to digital converters. And in the next lecture we shall consider digital to analog converters, which are commonly used as building block of analog to digital converters. So DA converters and some more different circuits which are required in embedded systems will be discussed in the next lecture. Thank you.